everyone. Thank you for coming to my presentation. And yes, my name is Jelena, and today I'm going to talk to you about security of machine learning and how we can attack network traffic classifiers using some properties of adversarial machine learning. So let's get started. First, a little bit about myself. Who am I? I basically did my studies, bachelor and master, in Novi Sad in Serbia. And then I went to Switzerland to do a PhD in informatics there. During my PhD, I also had opportunities to do 2 internships in Intel and IBM that were amazing experiences. And currently, I'm a postdoc, a postdoctoral researcher here in Institute of Telecommunications in Vienna. Starting from February, I'm moving on to the industrial settings as a data scientist, so I still stay here in Vienna, in beautiful Vienna. So a little bit about my work and my background. I'm very passionate about machine learning and security. For this reason, I'm working in machine learning for security domain, where I'm dealing with different aspects of malware detection, also face recognition systems, anomaly detection, failure prediction, and so on. I also find very, very interesting topic of security of machine learning, and within this context, I work on which attacks are possible to be performed on machine learning methods, how can we defend from these attacks, and also how can we increase trust that people place in machine learning through usually explainable machine learning methods. What I find particularly interesting is that when there are specifics of some application domains that kick in, and with respect to this, I'm very passionate about usage of machine learning in embedded and mobile systems. These are the systems where we need machine learning, but there are constraints there in terms of power, energy, the detection has to be fast, and so on. And the other aspect that I find very interesting is the use of machine learning in computer networks, in communication networks. So exactly this is what we are going to discuss today in the remaining of my talk. So coming to machine learning for security, why do we need machine learning for security? Well, machine learning for security is something that people rely more and more on. And the reason is that what machine learning can do is much, much more than just what humans can do, especially in terms of fast analysis of large amount of collected data. Also, in terms of predicting threats in huge data sets, all at machine speed. And finally, machine learning is able to detect attacks that were previously unseen on the security landscape. So it has a huge potential in doing all of this. So we think machine learning is good. We want to deploy it in practice. And the thing is that actually machine learning is being deployed more and more in practice. And also it is frequently used in an automated manner. Even more, recently it is more and more used to protect safely critical infrastructures. But one thing that we should not forget is that machine learning is essentially a software, and same as any other software, it has different vulnerabilities and problems that can be exploited. Also, recent research in adversarial machine learning has shown us that there are some inherent vulnerabilities and problems with machine learning that allow for attacks on it. Finally, machine learning is a black box approach, so we don't even fully get what it does and how it makes decisions it makes. Due to all of this, also security of machine learning is important, and we have to think about this aspect. Great. So we want to deploy machine learning in practice, and there are a couple of main steps to do this. The first step is usually training. In this step, we have a data set representative for the application that we are looking at, and then we do something that is called feature selection. It's a process in which we use the most representative features for the task of interest, and then we look into different machine learning techniques, and we say, with respect to the metric that we are interested in, this one performs the best, and we simply use this one, and then we use it in deployment stage, and we hope that this one now performs the best, and as we wanted it to perform in the application area. When it comes to the security aspect of the whole story, there are three important properties that we have to have in mind, and these are called SIA triad, coming from confidentiality, integrity, and availability. What are they, very briefly, is that basically confidentiality concerns with access to information being allowed to those people who have permission to do it. Basically, in the opposite way, if someone accesses information that was not envisioned to, this is break of confidentiality. Integrity deals with the behavior of the system, with the system behaving as it was intended to. And availability allows us to have reliable services to those users that are allowed to do so. So, what can go wrong with machine learning with respect to this, with respect to SIA triad, is that different things can actually happen. And the first thing that can happen is with confidentiality, that within this aspect I also consider in terms of privacy of machine learning method. So, first thing that can happen is model stealing. So, somehow, attacker can be able to duplicate the functionality of a machine learning model by somehow managing to steal the model and replicate it somewhere else. The other way that can go wrong is, again, at the deployment time, is called model inversion. In this type of an attack, the attacker is able to extract sensitive information that was used in the training phase. So this is something that the attacker shouldn't be able to do so, but it is now possible. The third type of attack that can happen here is a membership inference attack. And this attack refers to the fact that skilled attacker can understand if specific instance, maybe some patient record of a person he knows, is used in the training phase of the machine learning system. The next thing that can happen is related to integrity, and here we have a possibility of poisoning machine learning model with a goal to introduce backdoors or some kind of neural network trojans that can be later abused in the deployment stage. And what can also happen is evasion. Evasion attack is when someone manages to cause an attack on a machine learning system without machine learning system being able to detect it. Furthermore, it can happen poisoning with the goal to increase misclassification error on the machine learning system. And what can also be is that at the deployment stage, there is increased false positives. This means that attacker intentionally causes the deployed machine learning system to signal very, very frequently that there is something ongoing, while nothing is actually ongoing, with a goal to erode trust in this machine learning system so that eventually user says, well, this does nothing, I turn it off. So in the remaining of this talk, I will mostly deal with the evasion attack because it is very interesting attack. And it also happens at the deployment stage. But of course, all the other attacks are super interesting, and we can always chat maybe during breaks or so if someone wants to know more about some of the other ones. So, coming back to the previously seen machine learning system, how does evasion attack work on it? Well, basically, in this attack, we have an attacker that is interested in those instances that are misclassified as benign, confidently misclassified as benign by machine learning system, while at the same time having properties of an attack and actually delivering attack on the system. In the image classification domain, such instances are called adversarial samples. So how does this attack work? What happens here is that, what can happen here is that we, for example, have a stop sign that is to both human and machine learning system clearly a stop sign, right? But now attacker is able to introduce some malicious modifications in such a way that for human, this still remains clearly a stop sign, but in this case, machine learning system is strict to say, yes, it is a confidently sign to go, right? So this is a problem. And the other problem is that it was shown not just that these attacks exist, that these permutations can be created and added in such a way, but also that these attacks can be automated. There are ways to automate these permutations and add them to a stop sign. Further thing that was also shown is that these attacks also transfer between different machine learning techniques. So not that they work just for one classification system, but if you are able to create them for one, most likely they work also for the others. So how can we automate these attacks? Is it very complex? Do you need to be very skillful to do so? Not really. So these are all research efforts that are now publicly available. And there are basically three types of attacks. They are called FGSM, JSMA, and Carlini-Wagner attack. And they are publicly available. People can use them and play with them. What is interesting about these attacks is that they have different properties. For example, FGSM is the one that was introduced first. It is very fast, but sometimes in order to evade the system, it has to cause permutations that can be even visible to human eye, so not perfect in a way. But for example, the latest attack, Carlini-Wagner, it causes almost invisible, it causes minimum perturbations that to human eye are completely invisible. And that is a very powerful attack that now exists. The problem with this one, it is slowest in speed, but still, if there is time, the instances can be crafted. So as I said, these libraries with implementations of these attacks, so as with some proposed defenses, are publicly available, and almost everyone that has basic technical knowledge can take them and use them. What I find very interesting to use is Clever Hands from Google. Also, IBM has its own art tool where people can play with this. And there are also SecML and Fullbox that are research efforts from the community, but there are also other libraries. These are just examples of some. So these attacks transfer, right? But we also said that these attacks transfer, and there are two ways in which these attacks transfer. The first one is called Intra transferability, and it is referring to transferability between same types of machine learning systems. So for example, here I have a source machine learning system that is SVM. It is some local machine learning system where I can play with and try to see how it's going. And somewhere on the remote side, I have another machine learning system that I want to attack in some way. What happens here is that it was shown that the instance that is misclassified on my source machine learning system that I can create as an attacker is very likely misclassified also on the remote system of the same type, also on the other one and on the other one. So this is intra-transferability. The misclassified instances transfer between same machine learning technique. So this is worrying, right? But what was also shown is that cross-transferability exists. And this now means that if I have an SVM classifier where I'm creating misclassified instances, these attacks also transfer to other types of machine learning than SVM. For example, logistic regression, or decision tree, or neural network. So I can now craft my attacks even without knowing what is the type of machine learning that is used in the deployment. So what are the effects? How serious is this phenomena? In this figure, I basically depict the results of the recent research paper that actually introduced transferability as a phenomena. And here I have a target machine learning technique, what we discussed before. And on y-axis, I have source machine learning technique, what we discussed before. What we can see is that, for example, if target is SVM and source is SVM, there is 100% instances, misclassified instances, that transfer from one technique to the other. If source is something different, like, for example, logistic regression, there is 91% of instances misclassifying. So a huge number of instances is misclassifying. And also, if I have, for example, KNN, we again have huge number of misclassified instances. So this phenomena exists, and it is a serious phenomena that affects machine learning. The question rises of why such attacks happen. Why is all of this ongoing? And this is a difficult question, and the answer to this question is ongoing research effort. So there are all the times papers that further clarify why and how it happens, but just some arguments from papers is that basically what machine learning does is it takes some important features and overemphasize their importance for the detection outcome, so that in a way such that when an attacker modifies some of these sensitive features, even if it's a small modification, it can cause a change in the output. So it can cause misclassification in the output. The other argument is that since different algorithms somehow tend to use similar or same features as representative, it causes transferability phenomena to happen. So these are some of the explanations. So the question is, can we defend, right? Can we defend against these attacks? And if yes, how can we do it? First defense that people proposed is ensemble of classifiers. They said, okay, my SVM can be defeated. I put SVM, logistic regression, decision tree. I put 50 classifiers, and I hope some of them detects attack when it happens. But this actually doesn't work. The reason why it doesn't work is transferability. So it was very quickly shown that it's not enough to do so. And people said, okay, let's use adversarial retraining. Adversarial retraining, what does it mean is that, okay, now we know how do adversarial attacks look like. We can use some of the techniques to generate them, label them correctly, and then just retrain everything with this. This somewhat helps, but is not effective enough. And after some circles of this retraining, the system is not learning anymore, and there is also a problem with potential overfitting. So it's not the best one. Then people said, okay, let's use defensive distillation. This is a trial in a community to somehow smooth the decision boundaries of classifiers in those areas around the features that are considered important by the machine learning system. And this is shown to somewhat work, but not really, again, because of transferability phenomena. So people somehow protect their own machine learning system, but the attacker can always craft another attack on the local copy and attack the same one. The other way that people propose to fight with this is that we simply use the dimensionality of our input using, for example, PCA or some another technique. And in this way, the argument was that there is less surface for attacker to trick this system, so potentially the system is better. This is okay, but this raises a problem of a trade-off between robustness and accuracy, because in this way, accuracy of the system is somewhat affected. Another defense that also creates a trade-off between accuracy and robustness is regularization. And with this defense, what people did is that they said, well, okay, machine learning emphasizes the importance of some features. Let's penalize that. Let's not allow machine learning to do so, which is a good way of thinking, but then the accuracy is affected by this method. So one way or the other, none of these defenses is effective enough. And basically, there is a recent research paper that shows that all of these offenses can be evaded in some way. And the main reason is that the defenses are not effective enough. Also, people sometimes tried them just on one data set. When the other data set was used, defenses wasn't good anymore. Or they tried them with one type of attack, but not with all. So worked for one, not for the others. And overall, around the detection of adversarial samples, now we know that this is a more difficult problem than what people initially thought it to be. The other problem with security of machine learning is that most people actually focus on image classification domain, image analysis, and so on. And this domain shows us that vulnerabilities exist, but we don't really know how all of this affects other systems than image classification. So in the last couple of years, last 3-4 years, there are people who started looking into this, and they started looking outside of image classification only, mostly for malware detection domain. And also, we at TU look into network traffic analysis. So we provided some efforts into how can we defend our networks, and also what are the effects of these attacks in network traffic analysis. So this is now ongoing, and many people are trying to get and understand the effects of these attacks outside of image classification. But we look into communication networks. So the reason why we do this is that we think that detection of cyber attacks is extremely important, because there are basically billions of users of networks that rely on these security defenses to work well. The other thing is that the number of users of mobile devices and networks is constantly on the rise, and this opens new attack scenarios, while at the same time it becomes more and more complex to protect such a complex system. So our goal with the work we performed was to see, do network attacks transfer? So transferability phenomena that I mentioned before exists, but does it exist within machine learning based defenses that are used to protect our networks? And with respect to this goal, what we did is that we investigated first, does transferability phenomena exist here? Second, can attackers use it to bypass or basically degrade detection performance of our networks? And also, if it exists, what are the effects of intra and cross transferability? So the experimental evaluation we did with respect to this is that now it required that we put ourselves in the shoes of the attacker and try to understand what the attacker can do in this scenario. For this, we trained different machine learning systems, basically 6 of them, that are frequently proposed as those that are good, performing well on the detection of network attacks. And we train them, we train all these machine learning methods using a data set with representative network attacks. That is basically the one that researchers use in order to test different methods. So here, the evaluation scenario that we look at, what is happening here is that now we are the attackers, and we have the goal to find attacks not detected by remote machine learning systems. So we want to attack the system that is detecting cyber attacks somewhere else. And on our local side, we have one classifier that we can play with. So here, the attacker is saying, okay, I want to find that instance that is misclassified by my local system. And what is attacker thinking here? The attacker is saying, can I use some of the existing attack generation methods, right? Because we said there are 3 attack generation methods. Attacker maybe wants to use them here and just generate something, hope it misclassifies, right? But not really. This does not work because the domain of network traffic analysis has some specifics that are completely different than specifics of images. And just some of these specifics is that you cannot really modify any feature you want, same as you can do with image. And also, even if you modify those features that can be modified, you need to preserve the specifics of the attack, and the newly generated instance has to still conform to the network protocols. So we cannot just use image classification here. So the attacker here asks himself, what do I do? How do I manage to detect my remote system? And the attacker comes to a brilliant idea that instead of actually generating new different instances, he can use those instances that are already misclassified naturally by the machine learning system he has. So here attacker says, okay, I have a naturally misclassified sample on my local machine learning system. Let me see if this one, by chance maybe, or does it even transfer to the other systems, and maybe in this way I get lucky and I can attack the other system. So this is what we did. This is the check we did, and this is evaluation of Intra transferability, right? Because here we look into the same type of machine learning system locally and remotely. We also did evaluation of cross-transferability, asking the same question, but this time for different types of machine learning classifiers at the remote site. What we found out is that definitely these attacks transfer, and basically we can say that we see the effects of intra-transferability here. For example, if we again look into the SVM that we previously mentioned as a source and target, there are in our cases 96% of attacks that were transferring to the other type of SVM. Also, we observed that there are the effects also of cross-transferability. So basically, attacks do transfer across different types of machine learning, also for our network traffic analysis use case. And for example, if we have an SVM as a target and logistic regression as a source, there are more than 95% of misclassified instances. If we have, for example, KNN, there are more than 93% of misclassified instances. So these effects of transferability are visible also for us across basically all the used machine learning techniques. What we also understood for network analysis case is that ensemble of detectors do not work for us here, simply because the attacks transfer so much across different machine learning techniques that it does not make sense that you just take 10 of them and say, okay, these will somehow detect attacks. No, it's not enough. So, being this academic research, there are also some limitations to our results. We get great numbers, but there are still some things that should be improved here. And the first limitation comes from used data set. So this is a common property of research in security, that there is not enough publicly available data about attacks ongoing in networks. So we are restricted to use some older data sets that are publicly available and just for research purposes, for checking some basic properties. So basically this means that the data set we have and that we use for testing does not really contain the latest attacks on networks. The other limitation coming from the dataset is that we also use it we use the same dataset to test and train all of these methods. And the other limitation is the one that comes from naturally misclassified samples, using naturally misclassified samples here. So our attacker cleverly thought about this and said, okay, let me see if they transfer. And this is definitely a first step, because with these ones we see that the attacks transfer, but there is definitely further work needed in order to see if there are more clever ways to generate such instances, more than just using the naturally misclassified ones. So that brings me to first of my takeaways. And that is that security of machine learning is of growing concern. And the machine learning is so far proven to be vulnerable to all kinds of attacks. And it was also shown that some of these attacks can be automated and that they also transfer. So it is of growing concern for us. And the next important point is that reliable network traffic analysis is affected. And in our use case that we investigated, we could see the effects of transferability on detection of attacks. And we can also say, based on our analysis, that the ensemble that what people thought will easily resolve the problem by putting more classifiers does not work for us. Finally, so security of machine learning is a bigger problem than image analysis only or than network traffic analysis only. This is something that affects almost every machine learning system being deployed in practice. And now we know that all kinds of attacks and vulnerabilities are possible, but future work is definitely needed to understand how it works within other domains that are not investigated so far. So with this, I finish my presentation, and I'm looking forward to hear your questions. Also, if there are some questions that we don't manage to tackle now, we can maybe chat later, or you can get in touch via some of the social networks. Thank you. Thanks for listening.
Thank you, Milena.
Welcome.
Really great. Can we switch to the Slido? Yes. So just in case you forgot, join at slido.com, #WAD2019, and let's go through the questions. Ooh, a lot of questions. So the first one, to which kind of data have these kind of attacks been researched besides images?
Okay, so it's a very good question. Unfortunately, I would say 80% images, but there are other things also, as I tried to mention before. What I have seen so far is what I discussed within the domain of security. We have seen now malware detectors, mobile malware, PDF malware, and so on. We also work with network traffic analysis, but outside of this, there are some attacks that are shown for audio files, audio examples, and also for text classification.
Very interesting. Okay. I think the next question is probably pretty similar. So what are some examples where ML systems were attacked in the real world? Is there any examples?
Yeah. So there are some examples. There are, I think it was when the transferability was proposed, it was tested on 3 big cloud operators, and it was shown that these attacks actually work, and these cloud operators like Microsoft Azure, also I think it was was AVS, they were not able to correctly classify these images. But this is now image classification domain specific, is not for security related purpose. It was usually either a face recognition system where people were able to do targeted attack to be misclassified, as in one example, a famous actress Mila Jovovich was misclassified in this way with some random set of glasses. And so, yeah, so this big cloud.
Interesting. Okay. Yeah, really good question. Do you need access to the actual model for these attacks, or do they operate on the black box?
Okay, this is a great question. There are different severity of this attacks varies. So, of course, if you know everything about the model, that is what is called white box, the effects are much more severe. But they also operate on the black box, especially transferability, because for transferability, you don't really have to know what is the attacker running on the defense side.
Interesting. So the next one, regarding transferability of false classification, how large was the training set that allows to make such general statements?
Okay, so the data set that we have contains more than 20,000 attacks and more than 100,000 normal instances. This is not the largest, right? And that's why I said that the limitations of our work are limitations of our data set, that is the network traffic part. When it comes to the image classification part, and first the table with effects of transferability that appeared at the beginning, this is a research effort by Google. So they actually have a lot of data, and how they use it here is on an ImageNet data set that is a very big data set with containing a bunch of images. So yeah, I guess that this is a phenomena that is proven to exist.
Okay. So the next one, the difference between integrity and availability in machine learning are similar. Could you give an example? How are they different?
I think this is referring to poisoning. It was maybe slightly confusing to see in poisoning both in integrity and availability. Poisoning with respect to integrity means that the user got some kind of a network, either bought it or somehow did transfer learning on it and is using it in practice. But somehow another person was able to inject a backdoor in this network in such a way that now user thinks it's great, I enjoy my model, but it actually contains these backdoors, these triggers that can be activated at any time. That is poisoning in terms of integrity. Poisoning in terms of availability means that there is a running trusted classifier, but attacker is somehow able to inject poisonous instances in training set. So this running classifier is legitimate, but someone is trying to poison it with all kinds of instances, and once this system retrains, it will, by mistake, not knowingly, take into account this arrived poisonous training sample, retrain, and change its classification boundary unknowingly in such a way that now allows for misclassifications of all kinds. And by allowing this misclassification, the long-term such classifier performs badly because the attacker is able to somehow make it less trusted. And long-term, this poisoning will lead to lack of availability of this classifier because simply whatever it says will be wrong. So I took a bit more time to this because this is a good question and maybe I didn't clarify it well. I hope it's clear now.
Yes, I think it's a lot clearer now. Okay. We have a few more questions. Which of the attacks are the most frequent?
Yes, so I would say the most frequent is evasion because it happens at the deployment time. So somehow anyone can allow himself to send something to a model. And I would also say evasion for image classification purpose. So because if it's for some another security purpose, maybe you are not allowed to send instances to a system as frequently as you want. But one another side of these attacks is that we don't really know how many of them are happening in practice, because people are not willing to talk when and how often they are attacked by other people. So I would assume evasion for image classification, but also poisoning can happen if the system is online, learning online and retraining frequently.
Perfect. Yeah, maybe we could skip to the next one, so because that interested me as well. So are the features used in network traffic analysis designed by hand, or do you use neural networks or RNNs to generate them?
Okay, it's a super interesting question, and it shows, unfortunately, it shows where the computer vision is in terms of how things are happening, and where network traffic analysis is in terms of what is happening. So what is happening in network traffic analysis is that there are some features designed by hand, not even now, but through a period of designing machine learning systems, and we use those to protect systems. But of course, people in this community are aware of advances of neural networks and recurrent neural networks. So there are more and more research papers including them, dealing with them, comparing maybe newly generated features with the previous ones. And very important aspect here is that simple usage of neural networks as an end-to-end classifier within security domain is a sensitive thing to do. So there are still many people that prefer to know, okay, I use 10 features, but I know which ones, rather than using 1 million input features, having no idea which exactly, and in this way opening yourself to possible other attacks.
Interesting. Okay, let's go back to that question that we skipped. What are popular metrics for evaluating security of some ML systems?
Okay, super nice questions. Again, image classification accuracy is the primary metric here. In security, we deal with unbalanced data. So we have to look into much more than security. We look into precisions, recalls, F measures, ROC-out curves, PR-out curves. There is no really consensus, but people try to provide as many metrics as possible so that when the next researcher comes, has a basis to compare with whichever metric he or she now uses.
Okay.
Wow, so very nice.
Really detailed questions.
Yeah.
We're loving it. We have, I think, time for 2 more questions. Let's choose one. I think this one's really interesting, the one at top. If you were asked to hack Google image captcha, how would you go for it?
Oh, wait, if you're asking, okay, I think the limit would be timing. So these methods, they generate good samples that people are not spot to be somehow malicious, but they require a bit of time. So I think it would be an interesting challenge, but I would have to think about the ways and maybe sell it on a black market later on.
If you have ideas, please contact us.
Yeah, exactly. Next year, talk.
New business model. Cool. All right, last question.
Yeah?
Would you like to choose one?
So how would the neural, I'll choose this one.
Yeah.
It's interesting, has the most like. How would the neural network Trojan work? It is super interesting. How it would work is that someone would use, so the goal of neural network Trojan is that the network operates well on normal samples. So this is the limit, right? Because if you introduce a Trojan and then someone runs a network, does not classify anything correctly, this person throws your model by another one. So the limit is this. It has to perform well on benign samples. And how does a person do this is that trains on normal samples to create normal inputs, but then generates a set of specific inputs and marks them in a targeted way. And this person can choose to do, in this case, targeted misclassification, so that the samples that he trains on or she trains on are misclassified in a specific direction, or in just misclassification direction. So the attacker here gets a set of super specific inputs, says, okay, this is label cat, although it's something completely random. And then when you buy and run this network in your production system, it works absolutely okay on all kinds of instances. But now the attacker knows that if he uses that specific one that he crafted and injected previously, he will get a cat. no matter that this is actually something completely random. So this is the basic idea. I hope it's clear. But we can always discuss more details if I didn't address some of the questions in depth that was expected.
Exactly. So
Great.
thank you so much, Jelena. And Jelena will be here around. Find her, contact her, stalk her on social media.
Stalk is a bit exaggerated.
Follow her on social media. Thank you so much, Jelena.
Thank
Thank you. And give her, please, a big round of applause. Thank you, Jelena.